Hi guys, so in today's video we're going to be covering Euler's number. Now, if you recall, the expression that we had for compound interest was A of t equals P, which is the principal, the initial amount that you put in the account, times 1 plus the rate, the yearly rate divided by n, the number of times compounded in the year, to the power of n times t, t being the number of years. So again, P is the amount of money that you invested, R is the percentage rate as a decimal, T is the number of years, and N is the number of times that it's compounded in the year. So imagine that we're investing only $1. How would that change this formula? Well, the amount of money that we're investing is P, so it would just be 1 times 1 plus R over N to the power of N times T. And then imagine we take that further, and the interest rate that we have is 100%. So that would be 1 as a decimal, right? So how would that change the formula? Well, it would be 1 times anything as itself, so I'll just write 1 plus, and then the rate as a decimal would be 1. 100% is 1 over n to the power of n times t. And then imagine we are restricting t, and that the time, we're just going to make this simple and say that's only 1 year. How would that change the formula? Well, then the formula would be 1 plus 1 over n to the power of n times 1 for the 1 year. So that the final E of n, let's call this $1 investment at a 100% rate that was invested for 1 year. That formula, final one, would be 1 plus 1 over n, and then to the power of n times 1, which is just n. So let's elaborate on that and why we just did all that, right? Why are we looking at just a simple scenario of having an investment of $1 at a rate of 100% and for 1 year only? The reason why we want to investigate this is because this will actually give us a very special number. You can probably guess because of the title of this lesson that it is Euler's number. So let's go ahead and say that the amount of times that we are compounding this in the year, let's say that that was just 1, right? We give the interest on the account just 1 time in the year. So that would obviously make n be 1, and so then we would be doing 1 plus 1 over 1 to the power of 1, which is 1 plus 1, which is 2, and then 2 to the power of 1, of course, is just 2. Well, let's change that and say that instead of it being given the rate compounded yearly, we're getting this compounded semi-annually, so 2 times in the year. So that makes n 2, so it would be 1 plus 1 over 2 to the power of 2. So I'm going to use my calculator for that. 1 plus 1/2, which is 0.5, is 1.5, and then to the power of 2 is 9/4, which is 2.25. Okay. Let's take that further and now say that we're compounding quarterly. Well, then n would be 4, so this would be 1 plus 1 over 4 to the power of 4. What would that be? Again, let's just use our handy dandy calculator. 1 plus 0.25 would be 1.25. And then to the power of 4, we get 2.44, roughly. And then let's say we continue this further, right? We say we're compounding monthly, so n would then be 12. And for the sake of time, I've calculated these numbers, but I want to show you something. So the next one would be 2.6130. And then what if we are compounding this weekly, right? If n is 52, what would that be? That would be 2.6926. And what about if instead of weekly, we calculated it daily? If n was 365 and we calculated that, what would that number be? 2.7146. Okay, what about instead of daily, we calculated this hourly, every hour in the year, and n was 8760. Then our number would be 2.7181. Okay, so we started at 2 and we're getting what it looks like very close to 2.71-ish. And we're kind of getting a little bit larger, maybe going to 2.72, but it's the difference first was a little bit higher, and now it's almost staying the same number. Let's try every minute. What would that number be? 2.7183. And what about every second of the year? What would that number be? 2.7183. And of course, that's cutting it off at 4 decimal points. But what I want you to see is that the function approaching infinity, right? If that n number gets larger and larger and larger, what is the function approaching? What output does it approach? And it's, you see the last two, 2.71-ish, 2.7183. Now, this number, this roughly about 2.7183 number, is what is called Euler's number. And Euler's number is kind of like pi, in the sense that it is an irrational number. So in other words, there are numbers after this. Just like pi is a number, right? It's not a variable. We know exactly what the number is. We just use a symbol to represent that number, because that number is an infinite number. It does not stop, right? So usually we use about 3.14 to represent pi, but it has way more numbers than that, right? So, and the amount of numbers that we have in the back are forever forever continuing and not terminating. And Euler's number is the same in that way. It is an irrational number. Now, we can actually use calculator to make estimations with Euler's number. So I will show you. On your calculator, you want to find the E, which is right here. Okay, so in order to find Euler's number, right, you want to press E, okay? So if you want to see just what Euler's number is by itself, you can go ahead and press second to get to that E, and then put that to the power of 1, right? Anything to the power of 1 is what one copy of that number would be. So you could see that Euler's number, as much as we can fit on the calculator, is 2.7182811828, so on and so forth. Now, we're going to go ahead and evaluate some of these numbers, right? And all we're going to do is round to the nearest tenth. So e to the power of 7, so Euler's number to the power of 7 would be 1096.6. So we're just evaluating these, practicing using our calculator with it. E to the power of negative 5.6, e to the power of negative 5.6. Or, right, remember that any negative power we can bring to the opposite side of the fraction, right, and write it as a positive power. So we could either plug it in like that into our calculator, if your calculator, allows you to do that, or you can write it as a fraction, which would be 1 over e to the power of 5.6. And so that is, they did want us to round to the nearest tenth, but if I do that, I'm going to not have any numbers here. Rounded to the nearest tenth, this would be about 0. But let's go ahead and round to the nearest, thousands. That way we have a number. So it will be 0.004. Which, again, if we round to the nearest tenth, is about 0. If we follow the directions from the question. So go ahead and pause this video now and try number 2 on your own. Try finding these two. Okay, so anything to the power of 0 is 1, right? And then again, with your calculator, you can then find e to the power of negative 1.2 is 0.3. All right, so Euler's number, why is this number important for us, right? Pi is really useful when you're investigating circles, right? But what is Euler's number good for? Well, Euler's number is super important because it is a part of the formula that we can use for compounding interest that is compounded continuously. So if we're looking at the compounding, and like you saw in the investigation that we had for Euler's number, we derived Euler's number, or we found what, it was getting closer and closer and closer to the more and more we compounded an amount of money in the account per year. So the more and more compounding that we do, the closer and closer that we get to Euler's number. So Euler's number is a number that we can use for the formula to compounding interest that is compounded continuously. So not only every minute, not only every second, every millisecond, not even every millisecond. It's like continuously compounded. So the formula for that, I have it here, right? So the formula for compounding continuously interest is A of t. So again, our final amount A equals P, our principal, whatever the initial amount is, and then this is where it changes. Normally in here, right, we have something else for the rate, but for compounding rate that is continuous, the base is E, Euler's number, and then the power is R, whatever the interest rate is, multiplied by the time. Okay, so notice that N is not a factor because we are not compounding a certain number of times in the year. We are compounding continuously, so we're using E, Euler's number, as the base. So let's try a couple of examples, okay? What is the final amount for an investment of $1,200 compounded continuously at 5% for 7 years? Okay, well, as long as you see that they are compounding continuously, you're going to want to use this formula here, okay? So what is the final amount? So I'm solving for A, where my initial investment P is $1,200, and of course, E is a number, so that is not a variable. Remember that E is a number. To the power of R, the rate, of course, as a decimal would be 0.05%, multiplied by T, the time, how many years, which is 7 in this problem. So notice that now E is a number, so all of this are just numbers, so I can actually calculate this with my calculator. Again, remember you want to do exponents first if you're doing like multi-step, if your calculator doesn't allow you to enter it all together. So you'd want to do E to the power of 0.05 times 7 first, and then take that and multiply that by 1,200. Of course, you can also, if your calculator will allow you to, you can plug it in all together. So 1,200 times E to the power of, same thing, 0.05 times 7. Oops, let me get out of that. Okay, there we go. And it'll give you the same number. So our final amount, again, this is money, so round to the nearest hundreds, is $1,702.88. So there we go. That was our first example. Let's go ahead and try another one. So this question is a little bit different. It says, how much money should be deposited today in an account? So what they're asking you for is, what would P have to be? What would I have to initially put in the account today in an account that are in 7% compounded continuously? Again, so we're going to be using this formula instead of the formula that we learned in 9.3. And you want to accumulate, so you want the final amount in the account to be $10,000 after 8 years. So this is actually my A value. I want the ending result to be $10,000. I don't know my principal, my initial amount. That's what I'm trying to figure out. How much money do I need to input into the account? But I do know that this is compounded continuously, so it'll be e to the power of the rate, which would be as a decimal 0.07, times the amount of years, which is 8. Now, since this is multiplying, right, notice that the, and actually I could use square brackets so that you can, tell the differences. We're using multiple parentheses. It's nice to use a mix of square brackets and round brackets. So we're multiplying all of this to p. This is a number, right? It's e, which is roughly 2.7 blah, blah, right? And then to the power of another number. So this is a number, and it's being multiplied to the variable that I'm trying to solve. So all I need to do is divide by e to the power of 0.07 times 8, and then it'll cancel it out. Of course, if I do that to the right side, I have to do that to the left side. So in other words, p will equal all of this simplified. So let me pull out my handy dandy calculator, and I can add a fraction in. The numerator is 10,000. Oops, I think I put a few too many zeros there. That's 1,000, 10,000, there we go. And then in the denominator, e to the power of 0.07 times 8. So we have $5,712.09. That's how much you would initially have to invest in the account in order to get that $10,000 final amount if you are investing for 8 years at a 7% continuously compounded. All right, so go ahead and pause this video now and try 3 and 4 on your own. Okay, so let's take a look at number 3. If you deposit $4,500 in an account paying 3.2% interest compounded continuously, how much will the account hold after 36 months? Okay, so again, very important for you to look at how you're compounding. If you're compounding a certain number of times in the year, right, then you would use the other formula for compounding into a certain amount of times in the year, n. You would use p times 1 plus r over n to the power of n times t, where n is the number of times compounded. In the year. Now, if you're compounding continuously, right, then you would use the other formula that we just covered today, PERT, PERT. So P times E to the power of RT, okay? So this is for compounding continuously. So you would, if I tell you you're compounding semi-annually, continuously. Okay, if I tell you you're compounding semi-annually, then you're going to use this formula because you're compounding a certain number of times in the year. But if I tell you you're compounding continuously, then you're going to use this formula. Okay, so let's go ahead and find this answer. So what information did they give us, right? They told us that you deposit this amount of money in the account. So that's your P, your initial amount that you invested. They tell you that they're paying this percent interest. So as a decimal, that would be 0.032, and that is your rate R, and you're compounding continuously, so that tells you which formula you need to use, and they're asking you how much money you will have in the account, so you're looking for A if you invest for 36 months, which would be 3 years. Remember, in these two formulas, T is time specifically in years. So 36 months is 3 years, so that gives us T. So plugging everything into the formula, A equals 4,500 times E to the power of R, 0.032 times T, which is 3. And I just go ahead and simplify all of this. I can use my calculator and plug it in all at once, so I will do that. So 4,500 times e to the power of 0.032 times 3. And that amount is $4,953.42. 49.53.42. Okay. So let's move on to number 4. So on number 4, your investment earns this amount of interest. So R as a decimal is 0.0219. Remember, you move the decimal twice to the left and, add any zeros for placeholders if you need them. And it's compounding continuously. So I know I'm going to use my PERT formula. How much would you initially have to invest? So what is P to be worth? So to have a final amount of $5,500 in T 5 years. So I'm looking for my final amount to be $5,500. I don't know. What I need to solve for is the initial amount. And of course, the initial amount is being multiplied by e to the power of the rate as a decimal, 0.0219 times t, which is 5 years. Again, these two are multiplying together. So all I need to do is divide by e to the power of 0.0219 times 5. And you can simplify this first before you divide and, just divide whatever decimal is the estimation for this. But of course, by leaving this all intact and plugging it into your calculator, you're getting a more accurate number. Okay. And again, if if your decimal is, point something away because you rounded differently, it's not going to be an issue. Okay. So 5,500 over e to the power of 0.0219 times 5. Okay, so we have $4,929.55. Okie dokie. Awesome. So let's move on to our final question, the challenge question. Okay, so for the questions below, choose the appropriate word or notation to make the statement true. Okay. Euler's number is a real number, okay? It is a real number. In order for a number to be imaginary, remember, it has to have an imaginary component I, okay? And Euler's number is not. It's about 2.7, so it is a real number. However, the number is irrational, okay? It's never ending in the digits, and it does not repeat, so it is an irrational number. In the function f of x equals e to the power of x, e represents Euler's number. Now, what is the domain? Well, again, let's think about what e is, right? E is about 2.7. So this is really an exponential function, right, where the base is roughly about 2.7. For the sake of the idea that I want to point out, let's just say e is 2.7, right? We're going to round it. So remember that for exponential functions, if the base is bigger than 1, it is exponential growth. So this function where the base is Euler's number is an exponential growth problem. And remember that starts off slow and then quickly increases. Now the domain for this is negative infinity to positive infinity. You have an infinite arrow on the left, arrow on the right, negative infinity to positive infinity for x. Now, the y value, if you remember exponential growth, right, it is above the x-axis. So exponential growth will infinitely get close to 0, but never actually touch 0 or cross the x-axis. So the range is from 0 to infinity. All right, guys, so hopefully this extra topic on Euler's number is now helpful to add more variety to the types of problems that we can solve. So now we can also find, the amounts in accounts for interest that is being compounded continuously. All right, so I'll see you guys on the next one. Bye.